Hi there. Welcome back to this channel. We are going to be discussing the Malus's law. I've initially released a video that I prepared a slide for. I'm going to link it in the description below, so do well to see that video. But of course, I just want to show you the mathematical proof behind the Malus's law. Now, what does the Malus's law talks about? Now, you must first understand the concept of polarization. I've explained the Brewster's law. I'll also link that in the description. So now, what polarization is just about is that a ray of light that is traveling in different directions. Is that okay? Because an electromagnetic wave, so it is transverse, right? So it's going to be traveling in two directions. I mean, of course, in many different directions, but we represent them with these two planes where the electric field is traveling in the y plane and the magnetic field is traveling in the z plane. For this, my own case. So if this will be my y plane, this plane is going to be my z plane. And the direction of propagation is the x-plane. And that's what characterizes transverse plane. They travel in a direction that is perpendicular in all directions to the plane of their propagation. Okay, so now this guy I drew here is a polarizer, so which is a Polaroid. And an example is tourmaline, like I've already said before. So polarizer, this is my first polarizer. So we say polarizer 1, and let's call this P2, my second polarizer. So this is my second polarizer. I'll call it my analyzer because I want to use it to determine what I want to talk about here. So the first thing you should know is that Malus's law actually is represented mathematically as intensity is directly proportional to the square of the cosine of the angle between the analyzer and the plane of the wave that is traveling. Okay, so first get this, that this wave that is traveling is transverse, and of course it is made to pass through a polarizer. So by polarization, what the surface of the polarizer or the Polaroid is going to absorb this oscillation on the z plane and allow only the vibration on the y plane to pass through. So this second P, if left in the same plane of polarization, the plane of polarization is this y-axis, exactly. The plane around which the waves are allowed to pass through is the plane of polarization. So if this plane of polarization, if this polarizer is oriented in the same plane of polarization as the former plane, as the former polarizer, then this guy will also appear out of this polarizer in the same direction with the same amplitude, nothing unchanged, even though my diagram is not so depicting it. Okay, so it's going to be equal in amplitude, equal in everything, if provided that this guy is not shifted. But let's say this guy was shifted. Now this will be the consequence. So now I'm showing my polarizer now in full. I only showed the 2D plane now. So now this my polarizer, we call it the analyzer, right? So this is my analyzer I'm drawing here, exactly. So if my plane, if the wave, the oscillation that made it through the first polarizer, so let's call this is our first polarizer. This oscillation has made it past it and is now coming to the second polarizer. Okay. Now here's what happens. I could decide to rotate this my polarizer, my analyzer, if I rotated it such that the plane is no longer parallel to this plane. First, know that if I rotated it perpendicularly, perfect 90 degree to this guy, what would happen is that as this guy is coming here, it's going to be absorbed by everything here, everything on the molecules that make up the Polaroid. You should do well to see that video that I released on polarization so that you understand how this happens. I explain on the molecular scale. So let me just brief that. Now, the Polaroid is designed in such a way that if this was the plane of polarization, then what happens is that first, if this is the plane of its plane of polarization, the molecules that make up this guy are long chain molecules that will be arranged in a direction that is perpendicular to the direction of the plane of the polarization plane or polarizing plane. So if this is the polarizing plane, the molecules of this thing will be arranged in the perpendicular direction so that any wave that is traveling in that direction will be absorbed by them and they will not be allowed to go out. But any wave that is traveling in the opposite direction, perpendicular to them, is going to be the one that will what? pass through this plane of polarization. Okay, so that's the way it works on the molecular scale. So what happens here is that if you turn it to perfect 90 degrees perpendicular to that former plane, this guy, nothing will emerge out of this place. Nothing. Okay? No wave will be seen. But if I only rotated this guy a little bit, just a little bit, just a little bit, to show you that it's a 3D object, exactly. Now, I now rotated it. This guy was coming in this direction, remember? It's coming in this direction. But I've rotated this guy by some angle theta, and our guy is coming in this direction. Okay, if the wave was coming in this direction and I've rotated in this angle theta, then this equation holds true. Now let me prove that to you. What will happen is that the wave that will emerge from this place will have a lower amplitude than the wave that made it to the plane, to the polarizer. These are polarizer or a second polarizer or analyzer. Okay, so the wave that will make it out of here is going to have a lower amplitude than this. Let me prove that to you in mathematics. So let's say this was the plane of polarization. So let me bring the plane downwards. Okay, so it's just, this is my plane of polarization, this plane, this plane, this plane. Okay, now I have rotated this plane. If I rotate this plane rather in this direction, bring it down a little, you see that, you know that normally, mathematically speaking, I mean, in fact, generally speaking, it will not be as tall as this again. Just look at this, my markers. By the time I move this, if they were the same height, if I move this, you will see that they are no longer the same height, isn't it? Okay. So what happens is that, assuming that the wavelength, the ray of light rather, that is coming like this, is just has this amplitude A0. Okay. By the time it gets here, some of the amplitude would have disappeared, would have been absorbed actually. It's by absorption, it would have been absorbed. So this portion will be absorbed, this portion here will be absorbed. Then only this portion of wavelength, of amplitude rather, of amplitude, not wavelength, please, amplitude. This portion of amplitude will make it out. Okay? This portion. And this portion of amplitude, we'll call it A. This will be the A0, original amplitude. This is the new amplitude. Mathematically speaking, let's bring out the mathematics here. You see that we have a triangle here, isn't it? We have a triangle. So this length from here to here was what we rotated here. So from here to here is still amplitude A0. Does that make sense? Amplitude A0 here, we rotated it and it came here. So A0. Then from here to here is going to be our new amplitude. From here to here. Does that make sense? Alright. So if these are 90 degrees and our angle theta, which is the angle of rotation, the angle by which we rotated by, then it means that the cosine, because this is hypotenuse, this is adjacent. So the cosine of theta is going to be adjacent A over hypotenuse A sub naught. If this be the case, then A will be equal to A sub naught cosine of theta. Alright. Now, to now prove this law, remember that when we did waves, we said that the intensity of wave is directly proportional to the square of its amplitude. The square of its amplitude. If that be the case, then if I square both sides of the equation, then I'll have this. That is A squared equal to A sub naught squared cos squared theta. If this be the case, then A is always directly proportional to the square of A. So I is directly proportional to the square of A rather. So we have I, which is directly proportional to the square of A. We substitute. So I will be equal to I sub naught, initial intensity, cos squared theta. So that shows you. So by the time we impute this constant, so I becomes what? I naught cos squared theta. So that's the proof of Malus's law, that the intensity of light that comes out of a rotated analyzer is going to be less than the original intensity. All right. Do well to subscribe to the channel. God bless you as you share the video and subscribe to the channel, and God bless you. And as you pass your exams. All right.